Welcome to section 2.3, Venn diagrams and set operations. All right, starting off with objective 1, understand the universal set. So a universal set is symbolized by a capital U. And this is a set that contains all the elements being considered in a given discussion or problem. Okay. Objective 2 states understand the basic ideas of Venn diagrams. Now, Venn diagrams named for the British logician John Venn are used to show the visual relationship among sets. So here is the basic foundation or visual representation of a Venn diagram. The first thing you have here is a rectangle, and this rectangle is shaded in a darker gray font with a capital U. So this would be considered the universal set. Okay. Now, the circle on the inside is labeled with a capital A. So this would be the set A. And this set would be a subset within the universal set. Okay. Now we depict subsets by circles. Sometimes you might see other shapes like ovals represented, but in this course you'll see mainly circles. Okay. So just remember the universal set that represents the region inside the rectangle, the darker gray, and then the circle represents the subset. Now, the subset size, in other words, the circle size, does not matter. So if you make them big or you don't make all the circles the same size, that's fine. As long as they are within the universal set representing a subset, you're fine. Okay. Objective 3, use Venn diagrams to visualize relationships between two sets. So we're going to consider 4 basic relationships of Venn diagrams and their visualizations. Relationship 1, disjoint sets. Okay, disjoint sets. For example, you have 2 sets that have no elements in common, and these are called disjoint sets. So in our example here, we have 2 disjoint sets, A and B, and they're represented as circles that do not overlap. So that means no elements in the set A are elements of the set B and vice versa. So it's the first relationship you can have between subsets. The second relationship proper subsets. So if set A is a proper subset of set B, then we would use the appropriate symbol. A is a proper subset of B. So visually in a Venn diagram, if all elements of set A are elements of set B, and if an X representing an element is placed inside A, then it's automatically in set B because A is a subset of B, and that is a proper subset. Okay. The third relationship, equal sets. So if A equals B, then set A contains exactly the same elements as set B. And because all elements in set A are in set B and vice versa, then the diagram here is going to illustrate equal sets where A equals B. Then A is a subset of B and B is a subset of A. And the fourth relationship are sets with some common elements. So in mathematics, the word sum means there exists at least one. So sum means there exists at least one. So if set A and set B, you see both of them visually represented in our rectangle, have at least one element in common, then the circles representing the sets will overlap each other. So this region here in the center is going to be where all the common elements are between set A and set B. Okay, so those now are the four relationships between sets that we will see in a Venn diagram. So now that we have these relationships and we know what they mean, let's apply them to some problems. So in this guided example, we're going to use the Venn diagram to determine each of the following sets. Okay. So the first one is A. We want to know what are the elements in set A. Well, set A would be everything inside this circle, everything. So those would be the letters A, B, C, and D. They would be all of the elements in region 1 and in region 2. Okay. The set of elements not in B, the set of elements in B, but not in A. Okay. So the set of elements in B, but not in A. So we know the middle here in region 2 are where A and B are in common. We also know that this circle is set B. So set B has two regions, region 2 and 3, but the only region that contains elements in B but that are not in A would be region 3 with the element E. Okay. All right. The set of elements in U that are not in A. So U represents the universal set. Okay, so all of the elements that are not within the subset but contain that are elements within the universal set. So we want just the elements that are in U that are not in A. So the elements not in A are going to be E, F, and G. And so that would be region number 3 and number 4. Okay. Now we want the set of elements in U that are not in A or B. So A and B are the subsets within our universal set. So we want the elements that are not inside those circles. And the only elements that are not inside those circles, but inside the universal set, would be F and G, which is region number 4. Okay, let's do another one. We're going to use the Venn diagram to represent each set in roster form. So again, listing out all the elements with our braces. So we have our Venn diagram here. We have our two subsets A and B. I also see 8 and 9 within the universal set, but they're not inside the circle. So that means they're not contained within A and B. So for A, I want all of the elements in set A. So that would be the numbers 1, 3, 4, and 7. And then U would be the universal set. And the universal set contains now all of the elements that are within the subsets and not within the subset. So that would be the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right. Okay, so now we are going to move into some set operations. And these operations are the complement, the intersection, and the union. These are similar to arithmetic operations like addition and multiplication, just centered on sets. So in objective 4, we're asked to find the complement of a set. And the complement of set A, symbolized by A prime, so this here we just say prime, is the set of all elements in the universal set that are not in A. So this idea can be expressed in set builder notation as follows. A prime, or the complement of set A, is going to equal all x values such that x is an element of the universal set and x is not an element of A. For example, if we let the universal set equal 1, 2, 3, 4, 5, 6, and 7, and set C equal 2, 3, 4, 5, and 6, and we were asked to find the complement of C, the set C prime is going to contain all the elements in the universal set that are not in set C. And those would be the numbers 1 and 7. Okay. Another way to do that is to list out your universal set, then take out or cross out all of the elements that are in your subset. So that would be 2, 3, 4, 5, and 6. Then what is left over would be not C, or not in the set C, or the complement of set C. Okay. So visually in a Venn diagram, say we have the universal set, then we have a subset, and that's C. Everything on the outside here would be considered not C, or the complement of C. All right, let's do some examples. So here for number 3, we have our universal set, A, B, C, D, E. We have a subset AD, or A, with the elements AD, a subset B with the elements A, B, C. We are asked to find the complement of A and the complement of B. So let's list out the universal set and then determine the elements that are left over. So for A, we have A and D. Therefore, the complement of A would be the elements B, C, and E. Let's do the same thing for B, set B. So we'll list the universal set. Now the complement of B, we would find that out by crossing out all of the elements that are contained in set B, which is A, B, and C. So the elements not contained in set B would be D and E. Okay, let's do another one. We have our universal set, 1, 2, 3, 4, 5, 6, 7. Set A, 1, 3, 5, 7. B, 1, 2, 3. C, 2, 3, 4, 5, and 6. So the complement of set A is what we're looking for. So our universal set are the numbers 1 through 7. Set A contains the numbers 1, 3, 5, and 7. So the complement would be the elements 2, 4, and 6. Okay. And number 5, our universal set is A, B, C, D, E, F, G, and H. A contains the elements A, G, and H. So the universal is A through H. Set A contains A, G, and H. So the complement of A would be B, C, D, E, and F. All right. Objective 5. Find the intersection of two sets. The intersection of sets A and B, written as A intersect B, so this is the symbol for intersection, is the set of elements common to both set A and set B. So this definition can also be expressed in set builder notation as A intersects B is equal to all of the X values such that X is an element of A and X is an element of B. For example, find the intersection of the set 1, 3, 5, 7 and 1, 2, 3. The elements in common to the set 1, 3, 5, 7 and the set 1, 2, 3 are 1 and 3. That's what they both have in common, 1 and 3. Thus, the intersection between these two sets would be 1 and 3. Okay. Visually, if we have our Venn diagram, okay, and our first set was 1, 3, 5, and 7. Our second set was 1, 2, 3, and we know 1 and 3 is what they have in common. It would be represented as such. Okay, where 1 and 3 would be the intersection between the two sets. So it's what they have in common. All right, let's do some guided examples. So for problem number 6, we want to find each of the following intersections. So for the first one, the intersection between these two sets would be the elements that they both share. Well, the first set is 1, 3, 5, 7, 10, and the second is 6, 7, 10, 11. So I know they both have 10 and they both have 7. So their intersection would be the set 7, 10. For the next one, we have the first set 1, 2, 3, the second 4, 5, 6, 7. Now, both of these sets do not share any common elements. Therefore, we would have an empty set or the null set. For the third one, we have the set 1, 2, 3 intersect with the null set or an empty set? Well, nothing and something don't have anything in common. So this also would be the empty set. For number 7, we are given a universal set, a set A, a set B, and a set C. Our first question is asking us to find the intersection between A and B. So we want to identify the elements that they have in common, and that would be the numbers 1 and 3. Now we want to find the intersection between set A and the empty set, and this would be the empty set. Okay. All right. Objective 6, find the union of two sets. So the union of sets A and B, written A union B, is the set of elements that are members of set A or of set B or of both sets. So this definition can be expressed also in set builder notation as follows. A union B equals all x values such that x is an element of A or x is an element of B. So remember the empty set in intersection and union for any set A, if we found the intersection or the commonality between set A and the empty set, it would equal the empty set. Then for union, if we take the set A union the empty set, it would be set A, because we want all the elements that are in the first set and in the second set, or in both. Okay. For example, if we were asked to find the union between the set 1, 3, 5, 7 and 1, 2, 3, we would list the elements from the first set, 1, 3, 5, and 7, and then add to the list the elements in the second set that are not in the first set, giving us the union between both sets, 1, 2, 3, 5, and 7. So it's like combining both sets. So in these guided examples, we're asked to find the union between the two sets. Okay. So our first one here, this would be the numbers 1, 3, 5, 6, 7, 10, and 11. So I took all of the values from the first set and then added on any values in the second set that weren't in the first set. So the combination of both. For the second one, we'll take 1, 2, 3. Then we'll add on the second set, 4, 5, 6, and 7. Awesome. Then for the third, our first set is 1, 2, 3, union the empty set. So that would be 1, 2, and 3. Okay. Then for number 9, we want the union between set A and B. So I'll take the values between both sets. Now, if they both have a G and they both have an H, I don't have to state both of those twice. So I don't have to write 2 G's and then 2 H's, because those are the ones they have in common. So that would be in the intersection between the two. So I only have to write it one time. And then A union the empty set would be A, G, H, or in other words, set A. Okay. All right, objective 7. So some problems involve more than one operation. When this is the case, we're going to begin by performing any operations that are inside the parentheses. For example, if we were asked to find the following set, the complement of set B union set C, given the universal set, the set B, and the set C, we would first find B union C and then find the complement of that. So to find B union C, we first would list out set B and then set C. And since it's a union, we want all the elements that are in set B with all the elements that are in set C together, which gives us this 1, 2, 3, 4, 5, 6. Now we have B union C. But our question is asking us for the complement of this. So now we want all the elements that are in the universal set that are not in the union of set B and C. So we would take our union set, we would cross out all of the elements that are in the union. We'll take our universal set. Then we'll cross out all the elements that are in the union of B and C. So that would be 1, 2, 3, 4, 5, and 6. And the value or the element that's left over would be the complement. So in this case, it would be 7. So when you're doing these problems, I just want you to remember that union is like joining things together, like a marriage union. And intersection has two things overlapping, like two streets that are crossing over each other, like a crossing walk. Okay. So let's do these two examples. For number 10, we're given the universal set. We are given set A and we're given set B. And we're asked these two questions. First, we want to find the complement of the union between set A and set B. Okay. So first, let's find the union between set A and B. So that would be all the elements in A with all the elements in B. So that would be B, C, and E. Now we want the complement of the union of A and B. So now we want to determine what elements are in the universal set that aren't in this union. So we would have B, C, and E. So what would be left? A and D. Okay. The next one, we want the complement of A intersect with the complement of B. So we want to know what is the intersection between the elements that are not in A and the elements that are not in B. Okay, so we first need the complement of A. So we know, let me erase this for us. Okay, so we know set A is B and C. So the complement would be A, D, and E. Now the complement of B, well, we know set B is B, C, and E. So the letters that are left over are A and D. So we have the complement of A, we have the complement of B. So now we want the intersection. So now we want the elements that they have in common. And that would be the letters A and D. Awesome. Let's do another one. Number 11. So we're going to let U be our universal set, so all of the elements. We have set A, we have set B, and we have set C. So similar to the one that we did up above. So we want to find the complement of A intersect C. Okay, so let's first find what elements set A and C have in common. And that would be 3 and 5. Okay. Now we want to know what elements are in the universal set that are not in this intersection. And that would be the numbers 1, 2, 4, 6, and 7. So everything but 3 and 5. Okay. And then our last one here for number 11, we want to find the union between the complement of A and the complement of C. So the complement of A would be the numbers 2, 4, and 6. Okay. Those are all the numbers that are in the universal set that are not in A. The complement of C would be 1 and 7. Those are all the values that are in the universal set that are not in set C. Now we want the union between both of these sets. Okay, so we want all the elements that are in the complement of A and all the elements that are in the complement of C. So that would give us 1, 2, 4, 6, and 7. Awesome. All right, objective 8. Determine sets involving set operations from a Venn diagram. So elements of sets involving a variety of set operations can be determined from Venn diagrams. Now this Venn diagram here, which you can see a larger image in figure 2.17 in this section in the textbook, is used to determine the sets A through F as shown in the table below. So if I was asked to determine the union between set A and B, I would take all the elements in A or in B or both, all of them together. So that would be the elements in region 1, 2, and 3. If I wanted the complement of this union, I would be looking for all of the elements in the universal set that are not in this union. And that would be region 4, 666, because it's outside of the circles. For C, A intersect B. So whenever I see intersection, I'm looking for elements that are both in set A and in set B. So that would be where my circles overlap, which would be region number 2. Now, if I wanted the complement of this intersection, that means I want all of the elements that are in the universal set that are not in the intersection. So everything that's not in the overlap of these two circles. So that would be region 1, 3, and 4. Then for E, the complement of A intersect with the set B. Okay. So this means that I'm going to locate the elements that are not in A and are in B. Okay, so I'm going to eliminate not just the elements that are just in A or the elements that are in A and B. Okay, I am going to eliminate both. So the fact that they're in the A circle, I am removing them. So what would be left would be region number 3, because I had to take out their common elements as well, because those elements are contained in set A, and I want the complement of set A. And F, A union complement of B, set B. So these are elements that are in A or not in B or both. Okay. So I want everything that's in set A, not in B or both. Okay. And this would be regions 1, 2, and 4. Okay. So now let's use this information to answer some questions using this Venn diagram. The first one, A intersect B. So I want what is common between set A and set B. And that would be the element number 5, which is in region number 2. The next one, the complement of A union B. So first I want to find A union B. So all the elements in A and all the elements in B. So that would be everything in both circles, including what they share. Now I want the complement of that. So now I want the values that aren't in those circles. And that would be 17 and 19, which is region number 4. Okay. All right. I want the complement of A intersect B. So first let's find the not the complement. Let's first find the intersection of A and B. And the intersection of A and B would be 5. So now I want all the other values or all the other elements in the universal set that is not in region 2. So those would be the numbers 2, 3, 7, 11, 13, 17, and 19, which would be regions 1, 3, and 4. Okay. All right. The complement of A union B. Okay. So I want the complement of A with set B. Okay. So I know that A is going to be the regions 1 and 2. The 2 is also in B. So I can include it with the not A. So the only values that are just in A are 2 and 3. Now I want the not A, which would be 5, 7, 11, 13, 17, and 19 in union with set B, which would be 7, 11, and 13. So in combination, we would have 5, 7, 11, 13, 17, and 19, which would be regions 2, 3, and 4. Okay. A union B. So all the elements in A with all of the elements in B. So those would be the numbers 2, 3, 5, 7, 11, and 13, which would be regions 1, 2, and 3. And then our last one, A intersect the complement of B. So I want the elements of A, and I want the elements that are in the universal set but not in B, and I want the intersection between the two of them. So the elements in A are 2 and 3 and 5. Now, the elements that are in B are 5, 7, 11, and 13. So the elements not in B would be 2 and 3, 17 and 19. So the combination between the two would just be the numbers 2 and 3, which would be region number 1. Okay. Objective 9. Understand the meaning of and or. So when describing collections in everyday English, the word or refers to the union of sets, and the word and refers to the intersection of sets. You might have heard me say that throughout this presentation, but they have an objective specifically for it. So whenever we're talking about the union, it's one or the other. If we're talking about intersection, it's one and the other. Okay. To find the number of elements in the union of finite sets A and B, we're going to add the number of elements in A and the number of elements in B. Okay, so this is a new formula for finding the number of elements in a union, and this is objective 10. Once we find that number, we'll then subtract the number of elements in common between the two sets. Then we'll perform this subtraction so that we do not count the number of elements in the intersection twice, so what they have in common. So once for the number of elements in set A, and again for the number of elements in set B. The formula for the cardinal number of the union of two finite sets is the number of elements in the union of A or B equals the number of elements in set A plus the number of elements in set B minus the number of elements between the intersection of sets A and B. Okay. All right, so let's apply these to a couple of examples. So we're going to use the formula for the cardinal number of the union of two sets to solve the following exercises. So set A contains 33 elements, set B contains 15 elements, and 8 elements are common to sets A and B. How many elements are in the union of set A and B? So our formula is as follows. And we have the number of set A plus the number of B minus the number of the intersection of A and B. So the number of elements in A, they said, was 33. That was given here. The number of elements in set B is 15. And the number of elements they have in common is 8. So the order of operations when we have addition and subtraction, we go left to right. So that would be 48 minus 8, which would be 40. So there's a total of 40 elements in the union of sets A and B. According to factmonster.com, among the US presidents in the White House, 26 had dogs, 11 had cats, and 9 had both dogs and cats. How many US presidents had dogs or cats in the White House? So we're going to let set D represent the presidents that had dogs. And then we'll let set C represent the presidents that had cats. So if we set up our formula, we'll have D union C equals the number set D, that's the number of set C, minus the number of D intersect C. So the number of presidents that had dogs was 26. The number of presidents that had cats was 11. And the number of presidents that had cats and dogs was 9. So 26 plus 11 is 37, minus 9 is 28. So 28 US presidents had dogs or cats in the White House. For problem 14, we're going to continue to use this formula for the cardinal number of union of two sets to solve the following exercises. So for set A, we have 17 elements. Set B contains 20 elements, and 6 elements are common to sets A and B. How many elements are in the union of A and B? So we have the number of elements in the union of A and B. That's what we're looking for. And that will equal the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. So the number of elements in set A is 17, set B is 20, and they both have 6 elements in common. So 17 plus 20 is 37, minus 6 is 31. So there are 31 elements in A and B combined. All right. A winter resort took a poll of its 350 visitors to see which winter activities people enjoyed. The results were as follows. 178 people liked to ski, 154 people liked to snowboard, and 49 people liked to ski and snowboard. How many people in the poll like to ski or snowboard? So we know that because they said or, it's going to be a union. So let's first identify our sets. So we're going to let set A be the people who like to ski, and then set B be the people who like to snowboard. So the number of elements in set A union B will equal the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. So the number of people who like to ski is 178. The number of people who like to snowboard is 154. And 49 people like to ski and snowboard. So 178 plus 154 is 332 minus 49 is 283. So 283 people like to ski or snowboard. Awesome. And that concludes section 2.3.